All right, so a couple things. We finished up yesterday, intermolecular forces. We finished up things like that. It was yesterday when I made the videos. And so what we're gonna do today is we're gonna talk about some of the implications of what that stuff does, what the intermolecular forces, London dispersion, hydrogen bonding, et cetera, what it actually does and why we actually care at all. So here's what we're gonna do. If we have ourselves like a particle, two particles, let's say water, and so there's our oxygen, there's our hydrogen, there's our hydrogen, there's our water. And of course we have a partially positive, partially negative side holding onto each other there. Basically what's gonna happen is that's gonna create some hydrogen bonding there. This is so we have a hydrogen attached to an oxygen, strong partial positive, strong partial negative, strong partial negative, strong partial positive. Since it is a oxygen-hydrogen bond, big differences in electronegativities, we have hydrogen bonding going on there. Now, at a given temperature, this will either be a solid, a liquid, or a gas. So you kind of always got to think of those things interplay with each other. So temperature is the measurement of the average kinetic energy of a sample, how much average movemental energy there is inside of a sample. And the intermolecular forces is how much those particles are holding on to each other. So it's kind of like you can't just go, oh, hydrogen bonding, that means it's gonna be a solid because they're strong. No, at different temperatures, they're gonna have different amounts of movement, whether it is just vibrational movement, like a solid, or whether it's translational movement, like a liquid, or whether it is just they're free and they have a mean free path between them, like a gas. So you kind of always have to interplay both those together. And you also got to think about that just because it's hydrogen bonding and hydrogen bonding is strong, doesn't mean that it's gonna be stronger than the London dispersion forces. As we talked about last time, the iodines, which are just London dispersions, they're non-polar, they have become polarized, are solids at room temperature. Whereas some things with your hydrogen bonding, such as like alcohol and water, they're liquids at room temperature. Okay, with that being said, if something is going through translational movement, all right, so that means it is acting as a liquid. So what that means is that they are free to move around, but they're not separate from each other. The intermolecular forces are still holding on to each other. And so what you get is you get things moving as a liquid. Now, with things moving as a liquid, a term that comes up is this term called viscosity. And viscosity is the resistance to flow. And so it should make sense to you that the more attractive the forces are, the more resistant to flow they're gonna be. So some things are going to flow at a very slow rate, such as like honey. And we could say honey is gonna flow at a very slow rate, not because it's thick, but it's thick because there's lots of intermolecular forces. The molecules are also very big, which means lots of London dispersion forces, so intermolecular forces there. Some things will flow very fast, and these are things with less holding on to each other. And so if they're less holding on to each other, the gravity is going to allow them to pull a little bit quicker down, a little bit easier down. They're going to flow a little bit easier. With that said also, if you have a surface like that, and we have ourselves a drop of stuff right here, so what ends up happening is it actually makes a water droplet. It's gonna make a droplet of here. And the reason why is because all these particles that are at the surface here, yes, they have cohesion with each other. And so they're gonna cohese with each other and pull on each other. But then on top of that, remember there's particles underneath them as well. And so these particles underneath them, they have intermolecular forces with those guys as well. And so what ends up happening is they also pull inwards as well on this. And so what you end up getting is you get this, what we call surface tension. Surface tension. And so surface tension is this tension, this tightness of these molecules being held together at the surface here between the air and the fluid or whatever it is. And it's caused because of the intermolecular forces holding onto each other sideways as well as down as well. And once again, so like if you dive off a diving board and the water's perfectly smooth, you're gonna hurt if you hit that thing wrong, because that surface tension is fully intact, fully intact. And so as a result, all the energy, you going and hitting that, you've got to put energy in to break those bonds before you can actually go in and slow your impulse. This is why in diving, stuff like that, they will actually spray water onto the pool to break up that surface tension. Or like in a lot of like Olympics stuff, they have like bubbles. They'll have a bubbler at the bottom, and the bubbler will kind of make that surface bubble, so the person over rotates, they end up not hurting themselves really badly. A couple other things with this. When it comes to liquids, we can talk about the idea that inside of this liquid here, we're gonna have ourselves, we already said, particles that are attracting to each other. And so let's say I have water holding onto water, hydrogen bonding, which is just a glorified dipole attraction. If something is non-polar and gets put inside of here, this non-polar object will not get pulled apart. It will not dissociate into the solution here. And the reason why is because these waters are attracted to each other. They're attracted to each other. And when this new thing comes in, the water stays attracted to the other waters, and it just ignores this. There's nothing of interest in this at all. And so what ends up happening, it just kind of squeezes it out. It kind of just squeezes it out. And so kind of think about if you're hanging out with your friends, you're all talking, you're all hanging out, you have all this great conversation coming, and then somebody comes in and just kind of sits there, and they don't have any attractive forces. There's nothing pulling you towards them. They just sit there. Well, eventually, y'all could get up and leave and not even know that person was there. They're not going to dissolve. They're not going to dissociate into your group and kind of mesh into your group. And so this comes to this idea that like dissolves like. So you have to be polar-ish to be dissolved in something that's polar. Because even if you have something that is not water, but something with a positive, negative side, like an ionic compound or another molecule, as long as this positive can be attracted to that negative, and other waters, negatives, can be attracted to that positive, it'll be enough to hold it in place. It'll be enough to kind of pull it and kind of pull it into solution with it. Then on top of that, like dissolves like, so therefore a non-polar liquid can also dissolve another non-polar liquid. In fact, the closer they are in polarities, the easier they'll dissolve. So like a common example of this is people might get like oil stains on their shirts, or pin. People get pin mark on their shirts or whatever it is, they're writing with something, they accidentally hit themselves. What they can do is they can take like hairspray or rubbing alcohol, and they can use it to help lift that alcohol, that pin away, because they're closer in polarities than the water. The water is going to be really attracted to itself, and it's going to have a tougher time grabbing onto something that's just a little less attractive to. So like dissolves like, polar dissolves polar, non-polar dissolves non-polar. And then on top of that, we call this idea of like dissolving likes miscible. If something is miscible, then we say that it's able to be dissolved into that solution. Now, a couple other ideas. I know it's a longer video. A couple other ideas. If we have in here, let's say these fellers over here, these red guys are being held onto very tightly. These green guys are held onto each other kind of loosely, and of course they're also held on here because they're slightly polar, and we have different things of different polarities, different strengths in here. Well, when we begin to heat this up, what we're going to see is we're going to see the particles that have less attractive forces. They're going to be moving much freer than the ones that are being held in place. And that makes sense. The stronger the bond, the more energy is going to go in to make them move and become free. And so what you get is you get different vaporization points based upon the different attractive forces. The lower the attractive force, the quicker the thing is going to evaporate out. And so we can do that. One of the processes that we use this is an idea called distillation. Distillation. And so in distillation, perfect example of this idea called a still. Back in the day when people were making alcohol, moonshine, they're making alcohol back in the backwoods, whatever it is, they would be making this alcohol. They would take fruit, they would take whatever it was, and they would ferment it with yeast. It would end up building up a mash. They called it a mash. And it was a liquidy substance that had alcohol in it, water in it, stuff like that. Well, what they would simply do is they would collect that alcohol and they would heat, or this mash, they would heat it up. So this is just heat going in here. Well, then what would evaporate first? What would evaporate first is the alcohol. Alcohol, CCHHHHH, this is an OH. That's going to have a little bit of an attractive bond, but nowhere near as much as the water. Water has these two hydroxyl ends. It only has one hydroxyl end. This guy's going to be stronger held together. So the alcohol evaporates first. Then you'd collect it. And then it'd drip down. And then right here, you'd collect pure alcohol. And so you could collect this pure alcohol right here. So it's kind of neat. So you'd have this alcohol coming off right here. And then on top of that, you would heat it a second time. Because when you made alcohol back in the day, you would make methanol and you would also make ethanol. So these two substances here would get made. All right, so those two substances would get made. Well, you can see this guy is smaller than this guy by a whole carbon. So the result, even though they have hydrogen bonding, they also have some London dispersion forces. The bigger the molecule, the bigger the London dispersion force. And so what you'd have to do is you have to heat it a second time to then evaporate away the methanol. You cut that portion off. They call it the devil's cut. You cut the first portion off. The reason why is if somebody drank methanol, well, then they would go blind. It would destroy their liver and they would die. So distillation, we use it all the time to evaporate and clean things away, to clean out liquids and whatnot.